So I'm a graduate student at UC Santa Cruz, and this work is what I've been working on with one of my thesis advisors, Ruth Marie Clay, as well as Laura Perez, Hilke Schlichting, and Mickey Rosenthal. So the most common observational tracers of mass in disks are dust or gas, typically CO gas, as these are relatively easy to observe. However, we know that processes such as grain growth and drift should alter the ISM dust-to-gas ratio from typically assumed values. Furthermore, there are several lines of evidence that indicate that CO is depleted or missing in disks. You can also trace total gas mass in disks by measuring HD emission. So this probes the warm gas in disks and is a hydrogen molecule line. However, without Herschel, these measurements are not possible, although there are future prospects of doing this for some of the brightest disks with SOFIA. However, the question remains, how can we measure the total gas disk mass without an assumed tracer to H2 ratio? So one way that we may be able to do this is through analyzing recent multi-wavelength observations of disks in the millimeter. So here, I'm showing a representation of the disk TW Hydra and different observational wavelengths put together by Sean Andrews. And you can see that the same disk appears smaller in radial extent at longer wavelengths. And to introduce some terminology here, I refer the maximum radius in which you see emission at a given wavelength as a dust line. So this was inspired by ice line in disks. All right, so as others have suggested, these observations may be signatures of particle drift. So we all know that particles drift, and the rate at which they do so depends on their dimensionless stopping time. So for a stopping time less than 1, particles are relatively well coupled, and once you reach a stopping time of 1, you have your fastest drifters. So for the purposes of this talk, I will be discussing the regime with particle sizes less than 1, so they're relatively well coupled. Okay, so here on the right, I'm showing the same drift velocity, but reformatted to be a drift timescale. So this is in the Epstein regime for particles with stopping time less than 1. And so here I've just solved for the gaseous disk surface density. And you can see that you can solve for this parameter if you know the particle size at a given radius. And it also depends on this parameter V naught, which is the ratio of the sound speed to the Keplerian velocity. And for those of you that have worked on this before, you know that this has a weak radial dependence. So then if we know the particle size at a given radius, we can solve for the total gaseous surface density if we know something about the drift timescale of the particle. Okay, so to motivate my choice of drift timescale, here I'm showing a simulation from Till Bernstein, where he allows particles to evolve in the disk. And here we're plotting surface density, particle surface density as a function of radius and particle size. So you can see in the disk at late times, particle growth is limited by drift and collisional fragmentation becomes less important. So what happens here at this red line is that the maximum particle size at a given radius is roughly given by a particle whose growth timescale equals its drift timescale. And if you look at a given radius as a function of time, so here I've overlaid an earlier timestamp, you can see that this particle size decreases with time as larger particles drift inwards. So this means we can approximate the growth timescale, which is roughly the drift timescale, which is roughly the growth timescale, as the age of the system. And I won't discuss this now, but also note that the dust-to-gas ratio decreases with time in these simulations. Okay. So now that we have made an assumption about the drift timescale of these particles, if we know the maximum particle size at a given radius, then we can solve for surface density. So we can find these quantities through these observations. So if the wavelength that we're observing at corresponds to the particle size that dominates the emission at the disk outer edge, then we can say something about the particle size. And if we measure the radial extent of this disk, then we know the furthest radius in which particles of that size are present. So where these particles are the maximally sized grains. Okay, so in this new picture of disks, large particles of size S1 should be present throughout the disk until you reach a radius where their growth timescale is equal to their drift timescale, which is also equal to the age of the system. And if you pointed a telescope at this disk at observing wavelength roughly equal to S1, you should see a disk of this size. Now, when we move to smaller particles of size S2, they should also be present throughout the disk until they reach a radius where their timescales are equal, and the disk would appear radially larger at this wavelength. And this is also true for even smaller particles. So I'd like to point out that this method of deriving total surface density does not depend on a dust opacity. Okay, so in our recent paper, we've applied this model to 7 disks. So here I'm showing images of 3 of them, where you can see the disk size decreasing in radius as you move to longer wavelengths. So as one of the fundamental parameters in this modeling is the disk outer edge, we developed a new method of modeling disk visibilities, interferometric visibilities, using a Nuker profile. So this profile is nice because it can adapt to be either fit surface brightness profiles that are power laws, or self-similar solutions where you have a power law interior to a critical radius and then an exponential fall off. So here on the left, I'm showing a modeled interferometric visibility profile for one of our disks. And on the right, I'm showing simulated surface brightness profiles, where in blue, you can see that our method does a good job of picking up the disk outer edge, even if there are confounding dips in brightness. So now I'm showing the total gaseous surface densities that we derive from dust lines. So the black points here are dust for 4 of the 7 disks in our sample. So here the black points with arrows are the dust line derived surface densities. And what we've done here is scale observations, so blue is CO observations, and red is combined multi-wavelength observations of dust, where they've derived a surface density profile for these objects. So in the future, if we had many points, you can imagine fitting a surface brightness profile directly with those points themselves. But for now, we find that the points are actually well fit by rescaling these previously derived profiles. And actually, these are not all straight lines. You can see that they really follow the curve in the shape of these profiles. Okay, so now let's put these masses in context. So here on the left, for 2 of the disks in our sample, I'm showing our total gaseous surface density derived by dust lines in black, compared to previously tracer-derived surface density profiles and the minimum mass solar nebula. So the disks in our sample are 9 to 27% of their host stellar masses, significantly more massive than the minimum mass solar nebula. They are also 2 to 15 times more massive than estimates from integrated optically thin dust emission. And for the 3 disks with CO observations, resolved CO observations, they are 3, 40, and 115 times more massive than estimates from CO, which indicates that CO depletion may not be uniform across different disks. And this this shouldn't necessarily be surprising, as complications with CO chemistry, as well as difficulties with measuring the optical depth of these lines, means that CO is a difficult tracer of mass, which is something that has actually been known in the star formation community for a while now. Okay. So in our sample, we recover a correlation between disk mass and stellar mass. So here on the left, I'm showing dust masses. I'm showing this result from Pascucci et al. 2016, where they're plotting dust masses against solar masses for host stellar masses for disks in chameleon around stars up to around 2 solar masses. And if I take the relation that they found between dust mass and stellar mass, we recover this for our sample of objects that are disks around stars of similar masses. And actually, I was just chatting with Megan Ensdale, and she says that this really turns over at higher masses, which we may also be tentatively picking up. Okay. So all of the disks in our sample all the disks, here's the gravitational instability parameter, the Toomre-Q parameter for the disks in our sample, and the outer disk. So all of the disks in our sample respect the gravitational stability limit except for 1, which goes marginally unstable at certain radii. Interestingly, this disk was recently imaged with D-sharp, and at the radii where we see that it goes marginally gravitationally unstable, they've imaged rings instead of spiral arms, which is an interesting point. But the low Q values in the sample in general might indicate that at least some disks do not accrete efficiently. All right, so up to this point, we have not needed to assume anything about the dust surface density profile to derive our results. But now, given our results, we can use models of coagulation to determine a dust surface density profile, because for these maximally sized grains, their growth timescale is also equal to the age of the system. So here for the disk FT tau, in blue, I'm showing our total gaseous surface density profile, and in black, I'm showing the observed dust emission profile. So an analytic treatment of growth in these disks gives us this black dashed line, which agrees relatively well with observations. But we can also use our new input parameters and follow the dust evolution using Till-Bernstein's 2-pot-pi code, which we've done, and that is the gray dashed line here, which agrees with observations very well. We can also see where the particles end up in these simulations. So again, on the right, I'm showing a result from 2-pot-pi with our new input parameters, where I'm showing the particle surface density as a function of particle size and radius, and we see that the grains end up in the right locations to produce the observed dust lines that we see. So through this modeling, we derive dust-to-gas ratios in the outer disk that is typically around 10 to the minus 3, which is a very common expected outcome from models of grain growth and drift. I should also note that in these models, we initially start with a dust mass that is an order of magnitude higher than is presently observed, and that evolves to this value. So we can also use, since we have understanding of gaseous surface density and dust surface density independent of opacity, we can also use this method to empirically determine dust opacity. So now you might be asking about pressure traps. So what if there are pressure traps in this disk? So if a pressure trap is not efficient at trapping particles, then we wouldn't expect it to change this picture significantly. If there's a pressure trap, a strong pressure trap, anterior to the outer edge set by drift, then we also would not expect this to interfere with our observations, since our method for finding the disk outer edge is robust, even if there are confounding dips in brightness. What might happen is if there's a strong pressure trap outside of the disk outer edge set by drift, then it should be able to be seen in high-resolution, multi-wavelength observations of disks. So what that might look like is at the location of the pressure trap, large particles will be trapped tightly, and so you should see a thin ring of emission, then a relatively large gap, and a small inner disk with the outer edge set by drift. And then for smaller particles probed at shorter wavelengths, you'd expect to see a broader distribution of particles around the strong pressure trap, since they're less affected by drift in general, and then a smaller gap, and then a larger disk with an outer radius set by drift. So what if particles are actually aggregates? So here I'm showing a result from Kataoka et al. 2014, where I'm plotting the absorption opacity for different particles as a function of wavelength. And what they find is that porous particles are typically characterized in terms of their optical constants by their mass to area ratio, or their particle size times their filling factor. So here I'm showing the absorption opacity for grains of different sizes, but with the same size times filling factor mass to area ratio. So what this means is that the true particle size is roughly the observed particle size divided by the filling factor. And we know that the aggregate density is the density times the filling factor. So when we plug this into our equation for deriving surface density, we recover the same expression. So it's robust even if the particles are aggregates. Okay, so I should note that there are many more, or at least several more, disks in the literature that have multi-wavelength emission that seems to show this trend. So here I'm showing the disk UZ tau E with these radius points taken from Tripathi et al. 2017, and it appears to show similar behavior. However, many disks do not have published pre-reduced visibility data, so without being able to apply our specific method of finding the disk outer edge, it's not fully convincing, but this is something that could be applied to more disks that are already out there now. Okay. So another potential observational diagnostic of this method is to look at disk ice lines. So if drift dominates at the location of an ice line, your fast drifters will push the ice line inwards before they desorb, and actually your fastest drifters will stall. There's one place where you'd expect to see emission if drift is important. So what's nice about this is that as you vary CO abundance, your drift ice line stays the same. So while your ice line that you calculate from balancing adsorption and desorption flux onto a grain moves inwards as you increase CO abundance, your drift ice line is constant. So if drift is important, the ice line is an independent constraint on disk surface density. So I won't explain this plot at all now, but I'll just mention that in my 2017 paper, we discussed different ways that you could indicate or see if drift might be important in your ice line. And in the future, if we have a large sample of disks, another observational diagnostic that might be able to be approached statistically is that ice lines and dust lines should scale oppositely as a function of surface density. So if you move to more massive disks, your dust lines move outward while your ice line moves inwards. So that should be another signature of this model. Okay, and I think I'm out of time, so I'll leave you with my summary and take questions.
Thanks a lot, very interesting. So is there any question? Yeah, Simeon.
Interesting. So how do you determine the age of the disk, and do you take that to be the same as the star, and what's the
Yes, absolutely. So our surface density measurement depends literally on disk age, which we take from the literature for the objects in our sample. We talk a bit in the paper about the different age ranges that we see in the literature when you get different models. So we provide some errors based on age in that way. But that is one of the main sources of uncertainty that we have, is that for these young stellar objects, disk age isn't always well constrained. Although I have heard that relative ages might be well constrained, although absolute age is not.
I also have a question on, you briefly described the effect of rings and pressure traps, but it's not clear to me exactly how does this affect the specific results and assumption that you use. For example, in some of the disks that you've shown, we know that there are rings. TW Hydra has got rings, and then you mentioned also the case of UZ Tauri East, which is also complicated because it's a binary and it's got rings. So how does all this structure affect the assumptions that you have in your estimates?
Yes, so as I mentioned before, if there's a really strong pressure trap in the outside of where we'd expect drift to set the outer edge, that could interfere with where we're measuring the outer edge. But if you can disentangle that and see the place where you think drift is, which I think is possible, then that gets rid of a lot of the uncertainties. But I should say most of these disks that show rings have not yet been imaged at high resolution at multiple wavelengths. So it's a little bit difficult to tell how strong the pressure trap truly is. So there are, for two of the disks in our sample, indications of what I would say is a strong pressure trap. So one is for AS209, where we pick up a disk outer edge at 2 wavelengths that exactly corresponds with where there's a bump in CO emission and where we know there's a ring in D sharp. I also see indications of this for CY tau, although it doesn't have the same high resolution imaging. But for both of these disks, we're able to get dust lines interior to that region, which indicates either the pressure trap formed after some particles were able to drift in, or that they drift in fast. But if you can constrain it with a long wavelength point, you can get around some of the rings that might be present in the outer disk. But I'm very interested to see something like D sharp at more wavelengths, which will help constrain how much this impacts the model.
Okay, thank you. Other questions? Yes, Jeremy?
This is very interesting. I saw your paper just before this conference. Of course, it's a radical conclusion, and it needs to be tested. These increased masses. I don't know what the chemistry community would say about this, but just ask you a specific question. Maybe you answered this already, but if the dust opacity is causing this, on the optically thin assumption, is causing us to underestimate the disk mass. There's a lot more gas there than we think. Assuming the disk started out with a standard dust to gas mass ratio, such as we get in the ISM, the solids must be hidden somewhere. Now, is that because they're optically thick? And if they're optically thick, then does the assumption that that when you probe the disk at a given wavelength, you are seeing only particles of that size? If it's an optically thick layer, I'm not sure that follows.
Yeah, okay, so I'll do a few parts. The conclusion is radical in some ways, but I spend a lot of time in the introduction of my paper talking about why there's reasons to think that disks might be more massive, not the least of which is that we now have 4 imaged with spiral arms that are deep in the midplane and really seem to be gravitationally unstable. But I should also say that we're very much biased right now to the brightest disks in the sky that we can image at multiple wavelengths. So I'd be very excited to test this on disks that might be lower mass. Then
Where
the
are the
second,
solids?
yeah, the second point is, so when we derive these depleted dust to gas ratios, the models that we do to step through the evolution starts with an initial dust to gas ratio. So if the opacity is different, then we could use that to, well, we can use this model to constrain the opacity in some ways, definitely. But we could also, if we had what we thought was like a very robust constraint on opacity, then we can also tease out alpha, since that's the thing that we vary in our calculations for growth. So then onto your optically thick point. So finding the dust lines themselves is robust even in the case if it's optically thick. I'm very interested in doing modeling to make sure that we can still pull out a particle size with this. But if you have a sharp drop in emission, which is what we see, then it's hard for me to think of something that could cause that besides drift, because if you are an optically thick disk that transitions from being optically thick to thin, some kind of gradual decrease like that, you wouldn't expect to see the sharp dust lines that we observe.
Okay, other questions? Maybe Phil wanted to ask something?
Yeah, just a quick one. So I'm guessing that the high mass would be consistent for TW Hydra with the HD measurement. Are there any other disks in the sample where there's also an HD? Is there any other overlap?
So far, it's just TW Hydra. So the HD measurements give us a lower limit, and we're definitely consistent with that limit. Actually, not 2. It's a factor of 2 different. But no, so far we don't. Although, and I'm forgetting his first name, but his name is Pontopidian. He's proposing to use Sophia Hermes to look at least one of the disks in our sample, including HD 163296. So hopefully we will have more constraints with that, so we can.
I think there are only about 4 HD masses at the moment.
I think there are 3, but I could be wrong.
Yeah. Okay. But
Yeah. Yes, you're right. Handful.
Okay. Maybe Judith wanted to ask something.
Yeah, so this is certainly not an area of my expertise just yet, but judging by one of the recent talks, so if the Q value of 1.2 is still like the critical Q value with numerical simulations, then I think it's still useful to re-Q. I mean, obviously, if you want to form planets, you want to cool, or you want to.
Maybe I can say something about this. So in general, when we run these 3D simulations with thick disks, eventually the equilibrium Q is really Q equal 1. Now it's true that the tumor is for infinitesimally thin disks. So if you account for thickness, you would expect a critical value which is below 1. But at the same time, if you account for global high M instability, low M low M modes, then this rises the value of Q. So you have two competing things. Disks with a higher value of Q could be unstable globally rather than locally, but disks with thickness could be less unstable. So the combination of the two eventually leads to more or less 1. So I guess this is not too bad.
Yeah, and I'm really happy that there are lots of people here that work with gravitational instability. So raise the disk masses, do these disks.
Yes, I'm happy. Okay, so we can move on to the next talk then. Thanks again, Diana.